Thank you very much for that introduction. I'm going to kick off the session today with a look back on a roughly 20-year time scale so we can sort of better understand learnings from the past and a little bit of a peek in the future direction to see where some potential areas of research might be beneficial. Of course, I had in mind as I was putting this together the old adage that if we don't remember the past, then we're condemned to repeat mistakes that could have been avoidable. So I think it's useful to sort of set the stage for the other presentations with this kind of look back. And I'm going to be considering geothermal energy, enhanced geothermal systems, as well as unconventional oil and gas, because there's a lot of overlap between those two. So the question is where we're headed here and the timeline for this presentation. Now, of course, 2 decades is an arbitrary number. So I'm going to also consider some prior knowledge that predates that 2-decade threshold, which includes work, the Denver earthquakes, the Rocky Mountain Arsenal, work at the Rangeley Field, and also adjacent work in reservoir-triggered seismicity, so hydroelectric dam facilities and induced seismicity from that. In the early 2000s, we had people like Mark Zoback and Serge Shapiro who were publishing highly influential work that really drove a lot of the initial thinking on these things. And then we had some incidents, and this includes the Basel earthquake sequence in 2006 from Enhanced Geothermal System, and the development of traffic light systems in the geothermal industry that have been adopted and used as well for oil and gas work. Then things really came into sharp focus in the US mid-continent in the mid-2010s, disposal-related seismicity, and Bill Ellsworth was one of the key research figures during that period of time. And then mid to late, work really started to happen on hydraulic fracturing, as well as enhanced geothermal systems. And then we'll, as I said, we'll be finishing off with this Quo Vadis, and I'll share with you some ideas on what might be some fruitful new areas for research. So I'll go through this fairly quickly. I think people in this room are quite familiar, the Rocky Mountain Arsenal and the so-called Denver earthquakes. So these took place in the early 1960s. So fluid was being injected by the US Army Corps of Engineers. So this was disposal stream from weapons production. And what they were doing is disposing of large volumes of fluid directly into Precambrian basement, which seemed like a really good idea at the time. However, seismicity initiated shortly after they started this disposal process, and there was a remarkable degree of correlation between the ups and downs in disposal and the ups and downs in seismicity. So they curtailed disposal because of public pushback in 1966. And just over a year later, there were 2 significant earthquakes that occurred within the same zone that was lit up by the smaller events that correlated directly with the injection. Largest one of these was moment magnitude 4.8, and you can see some of the damage that was caused by that. So what this spurred was quite a remarkable controlled experiment. So as a scientist, I really appreciate the fact that there was an opportunity to undertake a controlled experiment on induced seismicity. This was a collaboration between the US Geological Survey and Chevron, and it was an oil field in Colorado that was known to have experienced issues with induced seismicity. And what was being tested at that time was the so-called effective stress hypothesis. And that's that as you increase fluid pressure in the subsurface, it reduces the normal stress acting on faults and therefore the fault strength. And so they built a model, they established what they thought was a critical stress, at which point they would start to see seismicity, and the experiment worked. So it really validated that hypothesis. So, and I think it's really important from thinking of prior knowledge for this crowd here to remember that reservoir-triggered seismicity, so in other words, seismic activity that occurs due to an impoundment, a reservoir impoundment behind a dam, and fluctuations in the water level in that reservoir has been well known and well established for many decades. And a prime example of that was the 1967 Koina earthquake in India, which was related to a monsoon, a big rise in the reservoir level and triggering of large induced events. And again, this is all thought to be due to pore pressure. So there's a pore pressure increase underneath the reservoir because of the change in the fluid level. So let's get into the last 2 decades. As I mentioned, Mark Zoback was a key figure in this. And one of the really influential publications was this paper in geology, which was expressing a counterintuitive idea that faults actually make the crust stronger. And they do this because they provide permeable pathways that maintain roughly hydrostatic conditions in the mid to lower crust. But one of the takeaways from this paper, or one of the insights, was that the Earth's crust is in a near critical state. And so what that means is that fault systems are at an incipient point of failure, so that a relatively small perturbation and stress is sufficient to reactivate the fault. So that wasn't the main point of the paper, but that was one of the things that really, I think, came across. Other work that was highly influential came from Serge Shapiro's group, Free University of Berlin. And they were really interested in looking at this from a diffusivity perspective. So these are so-called RT plots. They're showing distance from the injection source versus time. And what they found is that very commonly you could fit a quadratic envelope to these. And the parameter there is the diffusivity parameter that controlled the shape of the parabola. And then from that, they could infer things like permeability of the rock mass based on the feet of people living in the city of Basel. So they drilled a well to a depth of 5 kilometers well into the underlying crystalline basement, injected about 11,500 cubic meters of water. They were operating an induced seismicity monitoring system at the time. So the green graph that is shown below is from their proprietary monitoring system. I was also being monitored by the Swiss Seismological Service. So the black dots are showing events that were recorded by the Swiss Seismological Service. The largest event here was a local magnitude 3.4 earthquake, and it took place during shut-in. So what happened is the red light threshold got triggered on their traffic light system, so they shut in the well, preparing to flow it back. But during the shut-in, they produced this earthquake. Now, because this work was taking place in a densely populated area, a lot of people felt this magnitude 3.4 earthquake, and Basel Geopower decided to just pay out all of the claims. So they paid out $9 million in claims for property damage from this earthquake, but ultimately they were taken to court, and the $60 million project was curtailed as a result of this single event. So, and here's just a quote from Herring, who is CEO of Geothermal Explorers. If we don't get innovation for free, we have to work it out. The tremors we caused are a strong setback for deep geothermal energy. So, and there's been a lot of work that's happened since then, but I really wanted to point out the traffic light system that was being used, that was put in place during the development of this EGS system. It was a very sophisticated traffic light system in comparison to ones that we're working with today in the unconventional oil and gas world. So very briefly, I know this is not news to people in this audience, but things really came into sharp focus in about 2012 due to this dramatic increase in seismic activity in the US mid-continent. And fortuitously, it coincided with the US array, so deployment of dense seismometers throughout this area. So a lot of information was gathered that drove research as a consequence. And it was well established that the seismicity was being driven by large volume disposal of salt water associated with a dewatering play in Oklahoma and Kansas and parts of Texas. Here's a time history for it. So the green curve is showing the monthly number of earthquakes above magnitude 3. These earthquakes peaked in 2016 and then started to go down. Blue curve is showing the total injected volume in Oklahoma as part of this play. And the spin I would put on this is good news because it shows that mitigation is possible. So, and that the system behaves as you might expect, given what we know about induced seismicity and pore pressure. So it was actually the mid-continent induced seismicity that triggered the committee to produce a report. So this was came from the U.S. Senate, a request to do a report on induced seismicity from energy technologies. Here's a map that they produced. This is color-coded by the cause of the induced seismicity. It includes oil and gas extraction, wastewater injection. The pink color here, and there's just a single dot near Blackpool in the UK, is for hydraulic fracturing. And one of the key conclusions from this report is that you don't really need to worry about hydraulic fracturing. It's not going to produce any significantly large events. About a month after this report was released, the BC Oil and Gas Commission published a report from the Horn River Basin where they added 38 more events to the one that was in this report that they directly attributed to hydraulic fracturing. And that actually led to several years in the research community of debate about, well, who's right? You know, does hydraulic fracturing really produce induced seismicity of this magnitude significance or not? And we published a paper in 2016 in Science that was taken from the Fox Creek, the Kaybob Duvernay area near Fox Creek, where we closely studied a magnitude 4 induced seismicity sequence. We're able to pinpoint fault strands that were related to it. And in this diagram, these are two horizontal wells that were being zipper fracked, and the seismicity seems to delineate a fault that extends down into a basement. And Alberta's energy regulator responded very quickly to this situation and released through subsurface order number 2 a traffic light system for Alberta. And it's very simplified compared to the one in Basel, but it was put in place and has proved to be effective. Enhanced geothermal systems have continued to be in the news. So this is 2017 Pohang earthquake in South Korea, which has been attributed to an enhanced geothermal system development. So, and I show you this just to remind everyone that this is not an isolated phenomena that's just happening in Western Canada or a few different places. If we look at saltwater disposal, hydraulic fracturing, and enhanced geothermal systems, it's really a global phenomenon. So we're observing this almost everywhere where the right conditions exist. So I'll kind of switch gears a little bit, start to look at more contemporary research. There's been a fair amount of focus looking at trying to forecast maximum magnitude from an induced event. And the variable, the variable which is commonly used here is the net injected volume. So here are two diagrams that sort of take a look at this. I'm not going to go into the details, but you can see there are different curves that are drawn on here by different groups who have different models to try to explain this maximum magnitude question. But one of the key concepts is the distinction between runaway rupture and contained rupture. And simply put, contained rupture means that the earthquake is confined to the part of the fault which is stress perturbed by the fluid injection activity. And runaway rupture means that the earthquake starts likely somewhere within that zone, but then extends beyond the zone. So I'll share with you some ideas on some how to build on some of these learnings and where I think some potentially fruitful research directions should go. And we'll hear a lot more about other research directions from other presenters in this session. So just to list these off, one thing that I think our group and others have found is that seismogenic faults are often cryptic. So we go in with the expectation we have 3D seismic data, we can map all the faults that are important. That doesn't seem to have proven to be accurate, at least not in a granular sense. There does seem to be a change in what's called the B value. Again, I assume people are familiar with that, but I'll explain it briefly here. But is that really a robust indicator in real time? We talked a little bit about forecasting maximum magnitudes, but I would argue this only applies to contained rupture. So runaway rupture, if it extends beyond the perturbed zone, it's only limited by the size of the fault. And then some new work, we're finding that sealing faults that form pressure terrain boundaries might have elevated hazard, and trying to understand that. And then I'll say just a little bit about work that's happening on aseismic slip. So we know that natural earthquake systems exhibit both creep as well as earthquake type of activity. And there's really growing and strong evidence that this is also seen for induced seismicity. So just to work through this quickly, seismogenic faults, what you're looking at here is a topographic map, a structure map that's taken from 3D seismic data. There's an activated fault over here on the left, but the one that is most obvious on the 3D seismic is further to the right. And so we're thinking that larger faults may have cohesion, and that maybe we need to apply principles of structural geology to infer other subsidiary faults that are potentially subseismic in 3D. So I mentioned the B value. If we make a graph of the seismicity distributions, so here's earthquake magnitude and cumulative number of events, then these graphs typically show a straight line segment, and the slope of that gives you the B value. And what has been reported numerous times that there's a change in the B value that is concurrent with fault reactivation. So we have some explanations for this. We think the anomaly is the B value, the higher B value prior to fault activation. A B value of 1 is exactly what you see for natural fault systems. So that's telling us that we've actually activated a system. So the higher B value we think is happening because we're making measurements near the upper limit of the magnitude. So this is a so-called tapered earthquake distribution here. And I'm running out of time, so I'm not going to go into any of the details here, but it makes a big difference when you're estimating the maximum magnitude, whether you assume a conventional Gutenberg Richter or a tapered distribution. Some new work, which is just being published in the coming days in the journal Philosophical Transactions of the Royal Society. Using observations and modeling, we believe that a fault which represents a pressure boundary between high pressure and low pressure could actually be an elevated source of risk for induced seismicity. And this is contrary, or it amends slightly, the simple effective stress hypothesis, because the effective stress hypothesis tells you areas of high pressure, that's where you have the highest hazard. And what this is saying is that it's actually where there's a boundary between high pressure and low pressure where the hazard exists. So, and then finally, very briefly, we've done quite a bit of work looking at fault creep. So fluid pressure driving slow slip on a fault and how that connects to induced seismic activity. And some of the best information which is informing this is coming from satellite INSAR work. So I'll leave you with these key takeaways. Happy to go back and elaborate either during the question period or afterwards on some of the things that I covered. But key points here: induced seismicity has been documented since the 1960s, so it's not really a new phenomenon. But what at the time, the observations lent support for the effective stress hypothesis, so the importance of pore pressure. Research has surged in the last 2 decades in response to noteworthy induced events. So that includes the Basel sequence that I showed you, as well as this growth and decline in seismicity in Oklahoma. And I suggested a few potential areas for induced seismicity research where I think we could learn more. This is not an exhaustive list. There's lots of great work being done outside of this, but I'll just leave it for you to read, and welcome to answer any questions if there are any. Thank you very much.